we start with again numerical example on state space modeling. Till date we have seen the examples on lower order systems, but we know that practical systems are of higher order. For example, a power system model you can say it is 100 order, 500 order. So in that case it is possible for us to do the modeling of the system. Therefore today I am taking some examples on higher order system, along with this some other example which are important that I am also taking. Start with example 1. Suppose a 10th order differential equation is given as. So this is 10th order differential equations. Now here our main purpose is to determine the model of this differential equation in state space form. State space form, x dot equal to ax plus b, this form, this we want. Second, we have to draw the block diagram for this, and third, we required write the state space model in observable canonical form, that is we required in controllable canonical form, also in observable canonical form. So differential equation of 10th order system is represented as, this is 10th order system. So we have seen last time that whenever any differential equation is there, we have to apply Laplace transform. So here for this 10th order system we will apply Laplace transform. So applying Laplace transform to above equation we get this. Here this is 10th order, s raised to 10, s tend to 0, 10u equal to 0. Now the simplified form of equation is represented as, so what we have done, we have taken a ys common, this ys, this we have taken common and we have got this equation. Now from above equation ys by us, this is ys by us, we have got this equation. See here 10th order equation, and this minus 10 has come here this side. The companion form of state space model is represented as, now we have to represent this equation in companion form or controllable canonical form. This controllable canonical form, phase variable form, companion form, they have same meaning. In many of the textbook they are written companion form, in some of the textbook it is written as controllable canonical form. So now we have to write, already we have seen this part. So now we are writing down the state space model in companion form for this model. So we are written x1 dot, this one 0 1. So what we have done here, x1 dot equal to x2, that is why it is written as 0 1. Then here x2 dot equal to x3. So we have got 0 0 1. So here this element 1 corresponds to x3. Then x3 dot equal to x4. So you see here 1 is corresponding to x4. Similarly, if you go for this x9 dot, this x9 dot equal to x10. So you will find that 0 0 0 0 1, and this 1 has corresponding to this s10. And about this denominator we have to write down in a reverse order. Here this is 6, minus 6, 7, minus 7, minus 25, minus 25, and lastly this element is minus 7, and this B matrix 0 0 0 0 minus 10. So this minus 10 appeared here. And what do we do output? So output here y equals to x1, because the basic philosophy of companion form or controllable canonical form is based on output as a first variable. So here x1 equals to y, therefore you will find that y we written as 1 0 0 0 0 and 0 u. As I told last time, when there is when the order of the denominator is more than the order of the numerator, we get 0, but whenever both are same, then some elements will come. Here d is 0. Now just here, this is a block diagram of a controllable canonical form, that is companion form. So, as the order of the system is 10, therefore, how many integrators are required? So, we require 10 integrators. So, see here integrator 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 10 integrators. And see here this element 7, 100, 7, 8, 7, 1, 7, 25, 7, 6. So, you will find that this element are nothing but the coefficient of the denominator. So, see here we are represented like this. So, this is corresponding to x10 dot. So, this is nothing but x10 dot. So, x10 dot equals to 7x10, 100x9 like this. And what about this y equals to x? So, here x1 we have shown, and about u is x10 dot equals to minus 10 into u. So, it has been shown like this. So, ys by us, this is nothing but these particular equations. Now, about the observable canonical form, last time I have explained observable canonical form is also useful in state space analysis, particularly in checking observability. Also, when we need to design observer, this type of form is useful. Therefore, here we have written the observable canonical form for this particular system. But when we write the observable form, it is better first of all you write in a companion form and then you convert it, because it is very easy. So, see here A observable equal to transpose of A controllable matrix. You see here this is your A control matrix, and here this we have to make transpose of it. So, transpose of it means that this minus 6 which is here, it will go this side, you see here this minus 6. So, you will find that 0 0 0 minus 6 and up to 0 0 minus 7. Here we are simply make the transpose of A controllable matrix. Now, about the B observable. B observable means transpose of controllable matrix, means matrix which is obtained in controllable canonical form, that is C matrix. So, transpose of C matrix which is in controllable, which is in companion form or controllable canonical form is represented 1 0 0 0 0. So, you will see that this is 1 0 0 0 0, make transpose of it, and we make transpose, we will get 1 0 0 0. Now, about the C observable matrix. So, C observable matrix equals to B, a controllable transpose of B controllable canonical matrix. So, B controllable canonical matrix, this is transpose. So, what is the elements of B? B involved 0 0 0 0 0 0 minus 10, and we make transpose, you will get 0 0 0 0 minus 10, and here D observable is equal to 0. Now, we will take the another example. Till date what we have done, we have done that we have taken a particular state space model, and from this we have got some transfer functions. Now, here we have given the transfer function model, and state space model is also given, but there are some unknowns. So, we will see that in this example 2, here x1 dot x2 dot minus p1 minus q0 x1 x2 k1 k2 u and y equals to 1 0 x1 x2. So, in this example unknowns are minus p q k1 and k2, and transfer function model ys by us is given as 5s plus 15 s square plus 6s plus 15. So, using these two part we have to determine p q and k1 and k2. So, how will you do it? The first step is we will solve these equations. This x1 dot equal to minus p1 x1 plus k1 into u, and what is x2 dot? x2 dot equal to minus q x1 plus 0 into x2 plus k2 into u. Just see here this we are written, as this is in this equation in time domain. So, when time domain is there, if you want in S domain we have to take its inverse Laplace transform, or sorry, we have to take its Laplace transform. So, Laplace transform is s x1 of s, p x1 of s, x2 of s, k1 into u of s here, k1 u of s. Now here Laplace of this is x2 of s, and here one important thing that we have neglected the initial conditions. So here x2 of s minus q x1 of s plus k2 u of s. Now see this equation. So this is equations. So we have to solve this equation. So the best option is here we will find, we replace the value of x2 of s in this equation. Therefore this equation is represented as x2 of s equal to minus q x1 of s plus k2 u of s divided by s. So replacing x2 of s in this equation, we get s x1 of s minus p x1 of s. You just see here is p x1 of s, here we have replaced this. So you will find, you will get this plus k1 into u of s. So k1 into u of s. Now further we have solved. So how you have solved? This s is multiplied both side, this side as well as this side. When you multiply s this side, we will get s square x1 of s ps x1 of s minus q x1 of s k2 u of s and k1 s u of s. Now what we have done here, we have taken the terms related to x1 of s one side. So you see here x1 of s, x1 of s, x1 of s. So term related to this x1 of s, we have taken this side, and here terms with respect to u of s, we have taken this side. Now see here x1s by u of s will get sk1 plus k2 s square ps plus q. So this is the equation we have obtained, and you have given this equation. So you will find that there is similarity between these two equations. What is the similarity? This is second order, that is denominator is second order, numerator is also first order, and here denominator is also is second order and numerator is first order. So we can compare both these equations. So here we have written, and here y is by us, and here yt equals to x1 of t, because here you will find that y equals to x1 plus x2. So here that is why we have written here y of s equal to x1 of s, and this is ys by us like this, and now we have compare. So after comparison we will find that this is p, ps, and this is 6s. So p corresponds to 6. Now here q, this q corresponding to 15, and this k1 corresponding to 5, and k2 corresponding to 15. So in this way we have determined the unknown in the state space model. Now we start with the another example. Up till now we have seen the different form, companion form, that is controllable canonical form, then diagonal form, Jordan form. So there are different type of form can also possible. Therefore here I am taking one example. So by, if you solve this example, you are getting some different form. So just see this example. Now here I am drawing one block. That block is 1 upon s plus a. Now we will take another block 1 upon s plus b. Now I am taking another block s plus c. I will take another block 1 upon s plus d. Now here arrow I am showing. So here we applied us, and output is y of s, and here I am considering another block 1k. So here my aim is that the ys by us in this case we should get as k upon s plus a, s plus b, s plus c, s plus t. This is ys by us, and here we have to prove that x dot equal to minus d 1 0 0 0 minus 6 minus c 1 0 0 0 minus b 1 0 0 0 minus a, this is x plus 0 0 0 1 and output y equal to k 0 0 0 x1 x2 x3 x4. This same, this x is also like this only. This x dot means here x1 dot x2 dot x3 dot x4 dot. So here main purpose is that this is a plant or a system, and this system we have to represent it in this form. So this system can be represented in a companion form, canonical form we have seen last time. Now this is another type of form. So this is nothing but some series connection. If the series connection is there, we get x dot equals to like this. Now how to prove it? So we can prove by way that is here s plus a 1 upon s plus b, s plus c, s plus d. So s is there 4s, that means that there are 4 states, it means that there are 4 integrators. So here we have to assign states. So first of all we assign the states to this plant. So how do you do it? Let us see. 1 upon s plus a, 1 upon s plus b, 1 upon s plus c, 1 upon s plus d, this is k, this is y/s. This is input u of s. I am showing arrows have been shown, a, b, c, d, k, y of s. So this is y of s. Now we have to show the states. So normally we have seen, we have started all state with x1, x1, x2, x3, x4 like this. So here we will show a state as x1 of s. Now here integrator means it is x1 dot of s. So we can write this as x2 of s. Then here we write x3 of s, and here we write x4 of s. So we have written x1 of s, x2 of s, x3 of s and x4 of s. So now we have to solve it. So how to solve it? So we will find that here we write this block, this representation. So this can be represented as x1 of s divided by x2 of s, that is equal to 1 upon s plus d. Now you cross multiply it, then take its inverse. So what we will get? We will get x1 dot equal to minus d into x1 plus x2. See here this x1 of x1 dot, now d into x1. So when we go right side, it becomes minus dx1 plus x2. Now about this block. So this block is x2 of s divided by x3 of s, that is equal to 1 upon s plus c. So again we solve it, that is again we apply the inverse Laplace. So what we will get? We will get x2 of x2 dot equal to minus c x2 plus x3. And now coming to this block. So this block is x3 of s divided by x4 of s, that is equal to 1 upon s plus b. Now again we cross multiply taking inverse. So, what we will get? We will get x3 dot equal to minus bx3 plus x4. And now regarding this block, that is x4 s by u of s. So, x4 s by u of s we can write as 1 upon s plus a. Now, again we cross multiply it, what we will get? We will get x4 dot equal to minus a x4 plus u. So, here we got 4 equations, x1 dot, x2 dot, x3 dot and x4 dot. Now, we have to represent in a state space model. So, how do you represent it? We have x1 dot, x2 dot, x3 dot, x4 dot, that is equal to, right, x1, x2, x3 and x4, and this is terms for u. Now, here what is x1 dot? x1 dot equal to minus d x1 plus x2. So, minus d, so we will write here minus d. And what is the term for x2? It is 1, the rest of the elements are zeros, and corresponding to u element is also 0. Then about x2 dot equal to minus cx2 plus x3. So, we write as 0 minus c minus 1 0. Now, what about x3 dot? x3 dot equal to minus bx3 x4. So, here terms of x1 and x2 are 0. So, here I am writing down 0 0 minus b 1, and lastly x4 dot equal to minus a x4 plus u. That means here terms of x1, x2 and x3 are 0. So, I will do 0 0 0 minus a, but here u is there. So, u is 1, but let us see the about other x2 dot, x3 dot, the terms of u is 0. So, here only in x4 dot terms of 1 has come. So, u. So, what is the requirement? This minus d c b a 0 0 1. So, this we have automatically proved, and we will find that the important feature is that corresponding to each element a b c d we get the elements of 1 1 1. This is the arrangement. Similarly, if you increase the blocks, so we can get, let us say, d minus c. So, around this we will get 1, if f 1, like this we will get it. Now, about the output. So, output y equal to k into x1. So, we can write down as k 0 0 0 x1, x2, x3, x4, and definitely there is 0 into u. So, this is A, B, C matrix. Now, we start with another example on MIMO system, multi input multi output system. Most of the process control plant are of MIMO type. Therefore, if your system in a transfer function form, or you have a differential equation which is in a having a multi input multi output, in that case also we can determine the state space model of the system, and we will find one unique feature in this case. Unique feature is that if you take any model in a transfer function, we have 10th order, 100th order, but here in MIMO system, particularly when represented in state space form, order is always first order model only. There is no even a 1000 order system is there, in a state space order is always first order. Now, here we solve an example where we show that for a MIMO system also we are getting the state model in a first order form. So, we start doing this example. See, now here I am taking one block u1, this is one input, 1 upon s plus a. Now, here I am using 10, then here is a block I am showing, here is y1. Now, another input is coming, that is u2, and here the transfer function is s plus b, then here is 2. Now it is connected here. Now this u2 is connected to y1. Then we will take another input, say u3, and here the transformation block is S upon S plus C, and here a gain of 10, and it is showing to this summing block. This positive, positive, here is also positive, positive, and from where this path is coming from here, here, and it is connected here, and here is another connection, and this is output y2. So here output is y1, y2, input as u1, u2, u3, blocks are 1 upon s, s plus a, 1 upon s plus b, 1 upon s, s plus c, gain has been shown as 10 to 10. Now we have to solve this problem. Definitely one indicator is there, we have one state. If there 2 indicators are there are 2 states. So we will find that if you separate this equation, just now we have seen the last example. So it is possible that we can simplify this part and easily we can get the state space model. So how to do it? So here I am rewriting the block diagram again. Here I am showing 1 upon s, 1 upon s plus a, then 10, and there is this summing block, and this is y1. Here the thing is same, no change, that is 1 upon s plus b, these 2, and here it is connected like this. So here u2, u1. So here one change we have done, this 1 upon s, s plus b, it has been separated as 1 upon s, s plus a, u2s 1 upon s plus b 2, and lastly this is u3, it has been also been separated as 1 upon s, 1 upon s plus c, gain of 10, and here is a block, summing block. So you see positive values, and the other connections. So from where it has come? So we see that from this it has come from this side, this side. So here input u1 is connected to output y2. Now we have separated. Now we have to assume the state. So what happened? Here I have taken one state x1, and now here we can take state as x1 dot. So that x1 dot equals to x2. Then here after x1 x2, here is also an integrator, so we can take state as x3. Then coming here 10, we can take the state x4, and here we can take the state as x5. So here all the states has been defined. Now what we do? We have to take x1s by x2 of s, x3s by u2 of s, x4 by x5 of s, then x5 by u3. So all the equation we have to write, or individual transfer function we have to write. So now we write this. You see here x1 x2. So we write this as x1 of s by x2 of s equal to 1 upon s plus a. So equation we write, we cross multiply it, we will get x1 dot equal to minus a x1 plus x2. Now we have seen for this block. Now coming to another block, that is this part. This part is x2 of s divided by u1 of s equal to 1 by s. So you cross multiply it, we will get x2 dot equal to u1. So you can say this is equation number 1, I can take this equation number 2. So this portion has been completed. Now coming to this portion. So here x3 by u2. So x3s by u2 of s. So we write this as x3 of s divided by u2 of s equal to 1 upon s plus b, again cross multiplying and taking inverse Laplace, so we will get x3 dot equal to b x3 plus u2. So, this is equation number 3. So, this portion has been finished. Now, coming to this. So, here are two blocks, that is x4 with respect to x5 and x5 with respect to u3. So, we have to write down the equation for these blocks. So, we can write down as x4 s by x5 of s equal to 1 upon s plus c. Just here 1 by s plus c. So, you write it like this, and now we solve it. So, we will get x4 dot equal to minus cx4 plus x5, this is equation number 4, and lastly x5 by u3. So, we write this as x5 of s by u3 of s, that is equal to 1 by s. So, after solving we will get x5 dot equal to u3, this is equation number 5. So, we have got 5 equations, 1, 2, 3, 4, 5. So, now we have to solve this, that means we have to represent in a state space form. So, here we write this as equation as x1 dot, x2 dot, x3 dot, x4 dot, x5 dot, that is equals to, we have model x1, x2, x3, x4, x5 plus, now here how many inputs are there? You see here there are 3 inputs, u1, u2, u3, and outputs are y1, y2. So, here we can say the inputs are u1, u2, u3, and we have to represent output as y1, y2. So, this u1, u2, u3 corresponding to input, y1 and y2 corresponds to output. So, here this, here we write down as x1, x2, x3, x4, x5. Just check this. See here x dot, this is A matrix, this is B matrix corresponding input matrix, this is C is the output matrix. Now, we have to write down the elements in A, B and C. Just here x1 dot equals to minus a1 x1 plus x2. So, here we get the elements of only x1 and x2. So, we write minus a 1, and there are 5 variables. So, 5 elements, that is 3 additional elements 0 0 0. Then corresponding to x2 dot equal to u1. So, there are no terms there are no terms corresponding to x2 dot. So, we write down as 0 0 0 0 0, but here u1 is 1. So, here we can write down as 1 0 0, but whereas if you see the first equation I have written this one, but now we can write as 0 0 0. There are no elements of x1 dot corresponding to u1, u2, u3, that is why we written 0 0 0, and for this we have written 1 0 0. Now come to x3 dot. The elements corresponding to x3 dot is minus b x3 u2. That means we get only terms for x3, the rest of the elements are 0. So, we can write down as 0 0 minus b 0 0, and what about the elements for this in U matrix, that u1, u2, u3. So, we will get elements as u2 means 0 1 0. Now, corresponding to x4 dot. In x4 dot there are no elements of u. So, we can directly write down here 0 0 0, and now about this cx4 x5, the terms for x1, x2, x3 are 0. So, we can write down as 0 0 0, and this minus c 1, and lastly we come to x5 dot equal to u3. So, u3 is this, u3 is there, that means corresponding to this 0 0 1, and here we will not get any elements for x5. So, all the elements are zeros, and correspond. Now coming to the output y1 and y2. So, you will see that this y1, so y1 equal to 10x1 plus x3, then about y2 see here corresponding to x1 and x4. So, we write down the equation for y1 and y2. So, equation for y1 of s equal to 10 into x1 of s plus 2 into x3 of s, uses here 10 into x1, 2 into x3, and now corresponding to y2. So, the input is coming from this side. So, here x1 plus 10 into x4. So, we can write down as y2 of s equals to x1 plus 10 x4, and here in a state space form or output equation we can write down as this is x1 is 10, the element of x2 is 0, x3 is there, we can write down 2 0 0, and corresponding to this y2 of s, the elements we can write down as x1 is 1 0 0, and x4 term is there, that is 10, and x5 term is 0, and here there is no d is involved. So, 0 into u. So, you can again cross check it. So, x1 dot equals to a x1 plus x2. So, we written a1 1, then x2 dot equals to n, rest of the elements are 0, then x3 dot equal to minus bx3 into u2. So, we will find that elements of b, rest of the elements 0, ut we are represented as 0 0 1 0. Now, coming to x4 dot, the elements of u are totally zeros, whereas the other elements, that is x4 x2 x3 0. So, we are saying 0 and is c 1, and about the x5 dot equals to, we have say u3. So, let us say x5 dot, we can say, we can again check it, this is u3. So, we can write down as elements as 0 0 1, and about the other elements are 0 0. So, this is the state space model for MIMO systems. We can see there are some references, Ogatas, IIT Nakrat, then BN Sarkar. Thank you.